Okay, let's do our last section, section 5.8, exponential growth and decay models, and some specific examples, Newton's law, and logistic growth and decay models. So some applications related to exponential functions is basically what we're dealing with here. In this section, we'll address particular applications related to exponential functions. Populations obey a law of uninhibited growth, which leads to exponential functions. Populations that obey the law of decay also follow an exponential function. Here we've got growth, here we've got decay, so that'll have some impact on the style of the exponential function. Newton's law of cooling says an object cools down according to an exponential function, heats up according to an exponential function as well. And logistic models of population growth. We'll take a quick look at that as a finale. That's a little bit more than an exponential function. It involves exponential functions, but a logistic model is not an exponential function per se. So first definition, many natural phenomena have been found to follow the law of an amount A varying as a function of time according to the function A of t equals A sub 0 e to the kt. So we're certainly familiar with this stuff. We could take other bases of the exponential function other than looking at the natural exponential function, but this is tradition and computationally, this is more convenient. But this could be modified to deal with other bases. But the natural thing to do, believe it or not, is have base e exponentials. A sub 0 represents the original amount present, the amount present when time t equals 0, and k is some constant other than 0. If k is greater than 0, then the amount a increases over time, and that'll lead to the law of uninhibited growth. If k is less than 0, the amount decreases over time, and that'll lead to an exponential decay. In either case, when the amount a varies according to a model of this form, a of t equals a sub 0 e to the kt, then it's said to follow an exponential law. When k is positive, we've got exponential growth. When k is negative, we have exponential decay, which are really more common terms. The textbook tends to stick to this law of uninhibited growth, which is a reasonable thing to call it, but it's more traditionally called exponential growth. And were we to graph these, when k is greater than 0, we have exponential growth. We get a function that looks like this, only been graphed for t positive, but this is a piece of an exponential function. So we could see this extending. If we extended it to the left, it would asymptotically approach the t-axis, the horizontal axis. And here we've got exponential decay, also an exponential function. K is less than 0, the exponent is negative, also only graph for t positive. Were we to extend this, we'd see this extend upwards quite steeply as if we extended it to the left. But these, for physical reasons, are only considered for t greater than or equal to 0. The idea if we start with an initial amount at t equals 0, an amount a sub 0, and that amount grows when k is positive, or that amount decays away and diminishes if k is negative. A little biological example. Cell division is the growth process of many living organisms, such as amoeba, plants, and human skin cells. Based on an ideal situation in which no cells die and no byproducts are produced, the number of cells present at a given time follows the law of uninhibited growth. A population under these hypotheses grows exponentially, in other words. However, due to the finiteness of resources, after enough time has passed, growth at an exponential rate will cease and the growth rate will decrease. This we'll look at in more details in the logistic equation. These are topics you might encounter in an ecology class, by the way. these ideas from a math perspective, you'll see in differential equations. I have some differential equation notes posted online. Go to my online notes, and there's a hyperlink to rate problems. In Calculus 2, you'll explore exponential growth, exponential decay. Newton's law of cooling will appear there. You'll actually derive these using some calculus techniques based on certain physical hypotheses. You might see that, for example, Calculus 2 in section 7.2. I have a link there as well. So where these equations come from that's a job for calculus. What we will do is take these types of equations and manipulate them with the knowledge that we have. So looking at some examples from the section. Number 2 deals with growth of bacteria and tells us the following. The number n of bacteria present in a culture at time t measured in hours, obeys the law of uninhibited growth, n of t equals 1000 e to the 0.01 t. So here's the exponential function. They ask us, determine the number of bacteria present at t equals 0 hours. That would be n sub 0 in the notation we talked about. It'll be 1,000. So this coefficient will be the initial amount, as we'll see. What's the rate of growth of the bacteria? That was the coefficient of t by definition. What is the population after 4 hours? When will the number of bacteria reach 1,700? When will the number of bacteria double? So we'll start with this exponential function and answer each of those. The number of bacteria initially present is the number of bacteria present when t equals 0. We plug t equals 0 into the function, compute n of 0. That would be 1000 e to the 0.01 times 0. Replace the t with a 0. Gives us an exponent of 0. E to the 0 is 1. Anything to the 0 is 1, except for 0 itself. So we get 1000 out. And indeed, that's the coefficient that we have. This is n sub 0. Were we to write the function as n of t equals n sub 0 e to the kt. And this is exactly what we had in the notes. Oh, well, I guess we use the symbol a instead of the symbol n, but it's the same model. Part B, what's the growth rate of the bacteria? Well, the growth rate is parameter k in this particular expression. So it's the coefficient of t. In this case, the growth rate is 0.01. Might not be a bad idea to keep up with units. The units for that parameter, since t is measured in hours, the units for k would be per hour, 0.01 per hour. Then when we plug in t in terms of hours, we would have per hours times hours, and this would give us a unitless measure, and that's what we need to go into the exponential function. I don't think the book keeps up with units quite that carefully. It wouldn't be a bad idea, though. So this does come with units. But it's simply the coefficient of t in the exponential function. Part C, what is the population after 4 hours? Plug in 4. So n of 4 is 1000 e to the 0.01 times 4. That's 1000 e to the 0.04, at which stage I need a scientific calculator to evaluate the exponential function and plug it into that calculator. We'll get out 1041. Does that answer make any sense at all? The magnitude of it, maybe not so much, but remember, we started with 1,000 bacteria. 4 hours later, we're claiming we have 1041 bacteria. It is growth, so there should be more bacteria present 4 hours later than there was when we started. The magnitude of the number, I need a calculator to check the magnitude of it, but it is a meaningful answer. Part D asks, when will the number of bacteria reach 700? We have two variables, n and t. T gives the when. So this is a what is t question. Part C, we were told t equals 4 hours and asked a population question, asked about the n value. So we solve for n in part C. In part D, we have a formula, the model, and we want that to equal 1,700. So we'll set that equal to 1,700 and solve this equation for t. Well, t is stuck in an exponential function, so we'll have to get it out of that exponential function. How do you get variables out of an exponential function? By composing that exponential function with its inverse function, by taking a logarithm. We get variables out of logs by exponentiating. We did some of that recently. And we get variables out of exponents by taking logarithms. So we're at the stage where we wish to solve this for t. We're trying to get t by itself. It's been our strategy throughout for that. So let's get the 1,000 out of the way first. Let's divide both sides of the equation by 1,000, leaving us with e to the 0.01t equals 1,700 over 1,000. Simplifies to 1.7. Now we need to get the t out of that exponential function. You would do so by taking an appropriately based log function. This is a natural exponential function, so we'll take a natural log function. We'll take the natural log of e to the 0.01t. Right-hand side, natural log of 1.07. Numerically, don't know what that is, but we'll get a calculator out. Why did we do this? Because the log base e and the exponential base e are inverse functions of each other. So whatever the exponential function does, the log base e, the natural log function, undoes. These two functions compose to give the identity function, and out pops 0.01t. It is as if the log function base e and the exponential base e, it's as if those two cancel. Strictly speaking, it's not cancellation, it's composition of inverse functions. But again, as we saw previously in the previous section, I think it was, effectively those cancel. They disappear for sure. That's the reason we took the log function, to get rid of the exponential function. So we get 0.0t equals the natural log of 1.7. We're solving for t. Divide both sides by 0.01. That's 1/100th. So we're really multiplying both sides by 100. And we get t equals 100 natural log of 1.7. I need a calculator to see what that means. We will find that that value is 53. T was measured in terms of hours, so we get 53 hours. We were going from 1,000 to 1,700. The claim is it takes 53 hours. Does that number make any sense? These are really hard to judge in any numerical level of accuracy without a calculator. At least it's positive. If it was negative, we certainly have a problem. But numerically, I need the calculator to get this value out. Here's the precise value. Of course, that's not very meaningful to us, and that's a good time to numerically approximate. In part E, the question is, when will the number of bacteria double? Okay, we started with 1,000 bacteria. So this question is just like the previous question. It's a question of when is the population a certain size? In part D, the question was, when is the population size? 1,700. In this case, we want it to double from 1,000. So in this case, the question is, when is the population? 2,000. Now for some consistency here, the following should occur. If it took 53 hours for it to reach a population of 1,700, it's going to take, well, more than 53 hours for it to reach the larger population size of 2,000. How much more? That's too hard to tell. We'll ask the calculator. We can get precise values, but then we will numerically approximate. So in part E, we're actually computing what's called a doubling time for population size to double. And we want the population size to be 2,000, so we will simply take the function and set it equal to 2,000 and solve for t. We just did something almost identical to that. It's the same technique as part D. Divide both sides by 1,000. That produces a 2 on the right-hand side. We get e to the 0.01t equals 2 is the relevant equation now. We've got that t stuck in an exponential function. We'll take a log, take a natural log of both sides of the equation. Taking natural logs of both sides, we get the natural log of this, it's given here, equals the natural log of 2. What is the natural log of e to the 0.01t? 0.01t. The natural log in the exponential function combine, and disappear. Composition of inverse functions. To give us 0.01 t equals a natural log of 2. Divide both sides by 0.01 or equivalently multiply both sides by 100. And we get 100 times the natural log of 2 exactly, which is approximately 69 hours, a scientific calculator shows me. Does the answer 69 hours make sense? Yeah. Remember, it took 53 hours to reach a population size of 1,700. So it's not unreasonable that it would take 69 hours, a bit longer than this, to reach a population size of 2,000. The growth of an exponential function is complicated. Is this value precisely correct? That, I don't know. I just have to double check all the computations, but at least it makes sense. It's a bit more than 53 hours, as we would expect. So good idea to check and see if the answer actually makes sense. Or maybe it's a good idea to check and see if the answer is obviously wrong. It could be wrong and still make sense. But if it's obviously wrong, like a negative quantity when we have growth, and something's not right. Similar model, except this time we're going to have K negative. The physical situation concerns the amount of a radioactive material present at time t. It's modeled by an exponential function where K is less than 0 and A sub 0 is the original amount of radioactive material. So what we had with that bacteria example was exponential growth. What we will have with this radioactive material is exponential decay. Parameter K is negative this time because this represents a decay. It's the rate of decay. All radioactive substances have a specific half-life. We mentioned doubling time when we were doubling that population of bacteria. A half-life is the time required for half of the radioactive substance to decay. We computed a doubling time, was it like 60-something years in the previous example? We could also compute half-lives. It's computationally very similar. But since we have decay, then the population, as it were, the amount of radioactive material is decreasing instead of increasing. So it halves over a certain amount of time instead of doubling like the population growth model did. Carbon dating uses the fact that all living organisms contain two kinds of carbon. Carbon-12, nice, stable carbon, and carbon-14, a radioactive carbon with a half-life of 5,730 years. Carbon dating is useful in dating organic material, stuff with carbon in it that was once alive. While an organism is living, it interacts with the environment, and it has a constant ratio of carbon-14 to carbon-12. When it dies, that carbon-14 starts to decay away. That ratio changes. If you know how much carbon-14 was originally present, how much is present in a contemporarily measured sample, you can figure out how old that sample is, how long it's been dead. So this is good for dating things on an archaeological scale. 5,730-year half-life. For practical reasons, this is only valid for dating things. It's maybe a few tens of thousands of years old. So it's no good for dating dinosaurs that are millions of years old. But it is good for dating archaeological finds. Things on a scale of 10 to 20,000 years. Carbon dating is good. So the change in the amount of carbon-14 allows us to calculate when an organism died, how old a piece of parchment might be, for example. Let's do an example illustrating that. Where the story is iodine-131 is a radioactive material that decays according to this function. Amount present equals A sub 0, initial amount, e to the negative 0.087 t. Assume that a scientist has a sample of 100 grams of iodine-131. What's the decay rate of iodine-131? How much iodine-131 is left after 9 days? When will 70 grams of iodine-131 be left? And what's the half-life of iodine-131? Okay, this is computationally just like what we did in the bacteria model. The only difference is this coefficient of t, this time it's negative, and some of the other numbers have changed. The decay rate, part A, that's the parameter k. It is negative 0.087. If I were to keep up with units, t is measured in days, so this would be per day, would be the units of this. 1 over days would be the units, such that then the exponential function would be fed a unitless parameter, which it would need. Part B, how much iodine 131 is left after 9 days? They want to know what happens when we plug in 9. So we'll plug 9 in. We were told up here that we started with 100 grams. So we need to know that A sub 0 parameter is 100. Now the model becomes A of t equals 100 e to the negative 0.087 t. So we know what A sub 0 and k are. So I can go a little bit further with a model. A sub 0 is 100 grams. So plug that parameter in and then evaluate at t equals 9. Simplifies a little bit, and then I have to feed it to the calculator, and out from this comes the number 45.70. If A sub 0 was measured in grams, then this is measured in grams. So we started with an amount of 100 grams, and after 9 days, we have an amount of 45.70 grams. In part D, we're going to calculate the half-life. That would be how long it would take the initial amount of 100 to decay down to 50. How long is that going to be? Well, it took 9 days for it to decay down to 45.7. So less time, there'd be more present. Remember, we're talking decay here. So the half-life must be, I don't know, it's less than 9 days. After 9 days, what, 54.3% of it has decayed away, more than half has decayed away. So this amount of time is longer than the half-life. I can't tell precise values, but I can tell things like that. That takes care of A and B. Part C asks, when will 70 grams of iodine 131 be left? That's a when question. So that's a T, what is T question. So we'll set the amount equal to 70 grams in the function and solve for the variable T. When the amount is 70 grams, we'll have 70 equals to 100 e to the negative 0.08 t. Solve this equation. Same thing we did in the bacteria model computationally. Divide by the coefficient of 100. That produces 70 over 100, 0.7 on the right-hand side. Here we have an exponential function. Variable stuck in an exponential function base e, take a natural log to get it out of that exponential function. Natural log of e to the negative 0.087 t. The natural log and the exponential compose to give the identity. We're just left with the exponent. That's the whole reason we took a natural logarithm. Right-hand side, you still got the natural log of 0.7. Divide both sides by this coefficient, and t is exactly negative natural log of 0.7 divided by 0.087. This can't be negative time. The log, remember the logarithm of 1 is 0, and the log of a number less than 1 and positive is negative. So this log 0.7 itself is negative, and in fact, this is positive as it should be. I ask the calculator, it tells me it's 4.10 days. Part D is the same kind of question, but they want to know the half-life. Well, the half-life would be the time that corresponds to an amount present of 50 grams. We started with 100 grams. We want half of it to have decayed away. That's what half-life is. So we'll plug 50 grams in as the amount, and we'll set 50 equal to what the model presents at time t and solve for t. Same thing we just did, only the numbers different. The number on the right is now 50 instead of 70. We'll go through the same computations, divide by 100, take a natural log. That produces t equals negative natural log of a half divided by that coefficient. It's no coincidence that we're computing half-life and we get a natural log of a half in this. When we were computing doubling time in the bacteria model, there was a natural log of 2 in there, and that's not a coincidence either. I asked the calculator and it tells me that's 7.97 days. And we were just talking about this. We had, what was it? At 9 days, we had, was it 45 something grams left? More than half of it had decayed at 9 days. So we predicted the half-life would be less than 9 days. How much less? I don't know. Looks like it's about a day less. So 7.97 days is what the calculator produces for this number. But the computations are exactly the same as we've been doing. Newton's law of cooling also involves an exponential function. It's a little bitty bit different. Says Newton's law of cooling states that the temperature U of a heated object at a given time t can be modeled by the function U of t equals capital T plus U sub 0 minus capital T parentheses e to the kt, where k is less than 0. Capital T is the constant temperature of the surrounding medium, ambient temperature it's usually called, and U sub 0 is the initial temperature of the heated object. So the object starts at a temperature of U sub 0, warmer than the ambient temperature, the surrounding medium, which has a temperature of T. And then we have K less than 0. What's going to happen is this piece here is going to represent exponential decay. Then what's happening is the temperature is decreasing. The object's cooling off is what's happening. And it cools off according to an exponential decay model, this one right here, called Newton's law of cooling. So to manipulate this, we'll simply take Newton's law of cooling and plug in numbers. The story here is a thermometer reading 72 degrees Fahrenheit is placed in a refrigerator where the temperature is a constant of 38 degrees Fahrenheit. If the thermometer reads 60 degrees Fahrenheit after 2 minutes, what will it read after 7 minutes? How long will it take before the thermometer reads 39 degrees? Determine the time that must elapse before the thermometer reads 45 degrees. What do you notice about the temperature as time passes? What do you think you're going to notice? You put a warm thermometer in a cold refrigerator, the thermometer is going to have a temperature that decreases. That's going to approach the 38 degrees of the refrigerator. So we'll start with Newton's law of cooling. U of t equals t plus U sub 0 minus capital T e to the k lowercase t. Capital T is some constant temperature. In this case, it's that 38 degrees, the temperature of the refrigerator. That's the medium. Lowercase t is the unknown time. And, they didn't tell us k, but they told us some other information from which we can find k. So we measure temperature in Fahrenheit times in minutes. We're given an initial temperature of 72 degrees. U sub 0 equals 72 degrees, and a temperature of the medium, capital T, of 38 degrees. So we were given initial temperature of the object, the thermometer, and an ambient temperature, the temperature in the refrigerator of 38 degrees. So that allows us to at least substitute in for U sub 0 and capital T to produce this particular function. 72 minus 38 is 34. Yeah, that checks. So 38 plus 34 e to the kt equals U of t. So it's not exactly an exponential function because of the plus 38 that's involved, but basically an exponential function. We'll do quite similar manipulations to what we've been doing. Part A asks, if the thermometer reads 60 degrees Fahrenheit after 2 minutes, what will it read after 7 minutes? We still don't know K. K is some constant. Let's use this observation. Thermometer reads 60 degrees Fahrenheit after 2 minutes. Let's use that to find K. We know after 2 minutes, U of 2, the function would be 38 plus 34 e to the k times 2. So we've substituted in t equals 2 minutes, where time was measured in minutes. That produces this, and we were told at 2 minutes that temperature on the thermometer would read 60. So we plug 2 into the function, set that equal to 60. Here's an equation. The only unknown is k. This is how we'll find k. We'll subtract 38 from both sides, trying to get to K. That'll produce 34 e to the 2K equals 60 minus 38 is 22. 34 is in the way, divide both sides by 34. Now we've got the exponential function by itself. We're trying to get to K. It's stuck inside an exponential function, base E. Take a logarithm, base E. So take a natural log of both sides. The log and the E disappear. Composition of inverse functions, leaving us just with the exponent, 2K. Right-hand side has become natural log of 22 over 34. So we could simplify that if you like. We're trying to solve for K. So we'll simply divide both sides by 2 and get K as 1/2 natural log of 22 over 34. I asked the calculator and it tells me to 3 decimal places. That's negative 0.218. So there's K. Now we know U is a function of T specifically. So we've got all the parameters to express U as a function of T. We know capital T, we know lowercase u sub 0, and lowercase k. Lowercase t itself is a variable, so it changes. But all these other things were constants, and we found all of them with the information given. Now in part A, they ask us, given that information, what will the thermometer read after 7 minutes? They want to know what u of 7 is. T equals 7, plug that into the function, 38 plus 34 e to the negative 0.218 times 7. Calculator tells me that's 45.4 degrees Fahrenheit. Does that make sense? In detail, I don't know, but in a broad sense, it's been in the refrigerator longer than it was when it read 60 degrees. So the temperature it reads should be lower than 60 degrees. It satisfies that. If this was bigger than 60, something's obviously wrong. I could still have potentially done something wrong, but it's not obviously wrong. This is a reasonable answer in line with the fact that after 2 minutes, it was at 60 degrees. After 7 minutes, it's cooler still. At least we got that going for us. That takes care of part A. We'll carry this little function along with us. Part B asks, how long will it take before the temperature reads 39 degrees Fahrenheit? Okay, notice the refrigerator is set at 38 degrees, so it's cooling down towards 38 degrees. The temperature will be 39 degrees when T satisfies the equation, function evaluated at T equals 39. So set the temperature equal to 39, that produces this equation, and solve it as we've done previously. Subtract 38 from both sides, it just leaves a 1 on the right-hand side. Divide both sides by 34, producing this. Trying to get to T, it's in an exponential. Take a logarithm, natural log in this case, of both sides. Natural log of e to the whatever is the whatever. The exponent comes out. That's how you get to T. That's how you get it out of the exponential function again. And divide both sides by this coefficient to get T equals natural log of 1 over 34 divided by this thing here, divided by 0.218, and there's a negative sign that comes along for the right. Calculator tells us that is 16-something minutes, 16.18 minutes. Does that make sense? It was longer than it took it to cool down to the temperature we addressed in part A, right? So longer time, colder temperature. That makes sense. Part C, determine the time that must elapse before the thermometer reads 45 degrees. Okay, same kind of story. We'll set the temperature equal to 45, subtract 38 from both sides, produces a 7 on the right-hand side, divide by 34, take a natural log, that produces negative 0.218 T equals the natural log of 7 over 34. Ask the calculator, that tells us 7.25 minutes. So quite similar manipulations. The fact that the function has this 38 out front adds one tiny little step of arithmetic. What do you notice about the temperature as time passes? It gets colder. Not only that, it's going to asymptotically approach 38 degrees. The refrigerator was 38 degrees. The thermometer reached 39 degrees. after part B, after 16 minutes or so. How long will it take it to reach 38 degrees? Actually, according to this model, it will never exactly reach 38 degrees. It will asymptotically approach 38 degrees. That's what will happen. So they never asked you, when is it 38 degrees? That'll have no solution, in fact, because this exponential function has a horizontal asymptote of 38, and it does get closer and closer to 38, and it does never get there. There is no t-value for which the temperature will equal 38 degrees. And finally, the idea of a logistic model. We'll just take this as given, where this came from. We'll leave that to calculus or ecology in math biology. There's lots of population models and predator-prey models, and they all can be derived using calculus 1 or calculus 2. We'll just take as given that the logistic model expresses a population P after time T according to this formula. P of T equals constant C divided by 1 plus constant A times e to the negative bt for constant B as well. So A, B, and C are constants. A is greater than 0, C is greater than 0, and the model is exponential growth. If B is greater than 0, notice there's a negative sign that precedes the B, and it involves decay. So involves growth or decay depending on the sign of B. And they put a negative sign in front of it, yet it's in the denominator. So this is a bit trickier than the exponential function. We'll look at a graph down below. This number C is called a carrying capacity for the model. We have, in the case of a growth model, that as time goes by, maybe we even start right here. We start out with an initial population, and that population grows really dramatically. It grows roughly exponentially. This looks kind of like an exponential function. It isn't exactly, but it looks like one. But there comes a point in time where the growth starts to level off. And the thought here is the environment can only sustain a population of a certain size, and that size is C. So the population will reproduce and get bigger and bigger, but crowding becomes an issue. Limited resources becomes an issue. There's only a certain size of population of whatever organism this is that the environment can support. And what you'll see is the environment starts to level off, the population level starts to level off to this carrying capacity. On the other hand, if we took B negative, we would have, in some sense, a sort of a reflection of that curve. The curve would look something like this as time goes by. We're seeing a decay according to a logistic model. I prefer to talk about this in terms of populations growing and carrying capacities. This seems to be a timely point to indicate if you were looking at a pandemic and considering the number of people infected by a disease, it would follow, ideally, it would follow a curve like this. So this is a simplified model, but it's useful. You'll see this again if you take an ecology class, for example. So when B is positive, it's called a growth rate. When B is negative, it's called a decay rate. We get this kind of behavior for B positive and this kind of behavior for B negative. Some properties of logistic models are, we'll appeal to that graph. Again, the domain's a set of all real numbers. We exponentiated. There was no concerns over division by 0. There was some division, but it's not by 0. The range is the interval 0 to C. So if we'll look up here in both of these, 0 is a lower bound and an asymptote to the left in this model and to the right in this model. And we also had an asymptote at the top. So here's where we got two different horizontal asymptotes. That's something we have rarely, if ever, encountered in Precalculus 2. You'll see it in Precalculus 1. You'll see it in Precalculus 2. A tangent inverse function, an arctangent function, has asymptotes similar to this. In one direction, it has one asymptote, in the other direction, a different asymptote. But this has two asymptotes, two horizontal asymptotes. And one is 0, and the other one is the value c, in both cases, whether we're looking at exponential growth or exponential decay. So that tells us the range. There's no x-intercepts. The y-intercept is always what we get by plugging in 0. The function is defined at 0. P of 0 is the y-intercept, whatever that value that is. There are no horizontal asymptotes. There are 2 horizontal asymptotes, y equals 0 and y equals c, as we stated. P of t is an increasing function if b is greater than 0, and a decreasing function if b is less than 0. So we're kind of taking that as given by the textbook. We're not going to deal with these in depth, but these could potentially be added to the library of functions. But I think this is probably about the last we'll see of logistic models in the precalculus sequence. Though you will see it again in the calculus sequence, probably calculus 2. And they discuss another property. There's an inflection point where P of t equals 1/2 the carrying capacity. This inflection point is a point on the graph where the graph changes from being curved upward to being curved downward in the case of the growth functions. And it changes from curved downward to curved upward in the case of the decay functions. So it's growing and curving upward is how they've described this. Concave up is how you'll describe it in calculus. And it changes from curving upward to curving downward. And it changes right at that point. In economics, sometimes it's called a point of diminishing returns. But it's related to the bendiness of the function. It's related to the concavity of the function, is what you'll call it in calculus 1. And you have a similar behavior here, except this is curving downward and changes to curving upward, concave down versus concave up. And it changes right there. And where it changes is called a point of inflection of the graph. So it has that added property as well. And the graph is smooth and continuous with no corners or gaps, something best explored in a calculus class. This model is addressed in calculus 2. For example, follow the hyperlink to these notes, graphical solutions of autonomous equations. And these types of functions are encountered in this setting. You actually develop the functions from some more elementary hypotheses and properties of calculus. But for us, we'll just take, as a final example, we'll just take a function and manipulate it algebraically. Environmentalists often capture an endangered species and transport the species to a controlled environment where the species can produce offspring and regenerate its population. Suppose that 6 American bald eagles are captured, transported to Montana, and set free. Based on experience, the environmentalists expect the population to grow according to the model P of t equals 500 divided by 1 plus 83.33 e to the negative 0.162 t. T is measured in years. So for our purposes, this is the function we're interested in. Determine the carrying capacity of the environment, part A. That would be this parameter in the numerator as we defined it. What is the growth rate of the bald eagle? That would be this parameter here, 0.162, based simply on the location of it. That's what we called the growth rate, provided that parameter B was positive. B is positive. The negative is not part of the B parameter. What's the population after 3 years? We plug in t equals 3 and get the calculator out. When will the population be 300 eagles? Set this equal to 300 and solve for t. How long does it take the population to reach 1/2 of the carrying capacity? That'd be where the point of inflection is, by the way. Okay, so in a logistic model, we had A, B, and C as given here. This was the statement we had in the notes. So in this case, we have C is this number, C is 500. A is the coefficient of the exponential, so A is 83.33. And we had e to the negative bt. Here we've got e to the negative 0.162 t, so b is 0.162. So the carrying capacity is C equals 500. Units are eagles, I guess, if we keep up with the units, but that's population size. In part B, they want to know the growth rate. The growth rate is parameter B itself. So the growth rate would be B equals 0.162. It would have to be expressed in terms of per years, since T was measured in years if we kept up with units there. Part C asks us, what will the population be when T equals 3 years? So we'll plug T equals 3 in. And at P of 3, we get 500 over 1 plus blah, 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 plugging in 3 for T. Simplifying a little bit, negative 0.162 times 3 is negative 0.486. Beyond that, I'll just rely on the calculator. It will tell me that's approximately 9.57. We're counting eagles here, so we want something that's a whole number. So if we round this, we'd round it up to 10. So I'd say the eagle population is 10 at this stage. So we've seen growth. We started with, wasn't it, 6, right? We started with 6 eagles. After 3 years, population has only grown by 4 to a population of 10 eagles. This model assumes no death, so there's some unrealistic oversimplifications in the model, but anyhow. In part D, they want to know when the population will be 300. Well, it took 3 years to reach a population size of 10. So I'm expecting it could take a while to reach a population of size 300. We'll set the population equal to 300 and solve for T. Okay, the manipulations are a little more complicated this time, but same strategy, trying to get T by itself, solve for T. We could divide both sides by 500. That produces 300 over 500, or 3/5 on the right-hand side. We've got fractions on both sides. Let's take the reciprocal of both sides, or cross multiply if you like. That will produce reciprocal of the left-hand side is this stuff with the exponential function. Reciprocal of 3/5 is 5/3. So we've got this equation, and we've dealt with this equation before. This is the same style of equation we had with Newton's law of cooling. So we can solve this. Trying to get T by itself, subtract 1 from both sides. We'll lose the 1 here. 5/3 minus 1 is 5/3 minus 3/3 is 2/3. So we have 2/3 out on the right-hand side. Divide the 83.33 out. Divide both sides by 83.33, produces this ugly numbers here. We've got now the exponential function by itself. So we need to get to T. It's inside an exponential. Take a natural log, as always. Natural log of e to the whatever equals a natural log of this stuff on the right-hand side. Natural log of e to the negative 0.162t is negative 0.162t. Right-hand side, we get the natural log of 2 divided by 3 times 83.33. I suppose it's 249.99 for fans of numbers. And all we have to do is divide by this coefficient of T, negative 0.162. And we get T is right-hand side divided by that 0.162. There's a negative sign out front. And now I feed it to the calculator, and the calculator tells me that's 29.8 years. So it takes 29.8 years for the population to reach 300. So it took 3 years for it to reach a population size 10, and it took only another, roughly 19.8 years to reach a population of 300. So it's actually started to grow quite well. The carrying capacity was 500, as we observed above. In part E, they want us to know when the population reaches 1/2 of the carrying capacity. The carrying capacity is 500, half of that is 250. So their question is, when does the population reach a size of 250? We just saw it reaches a size of 300 at, what was it, 29.8 years. Reaches 300 at 29.8 years. So how long will it take the population to reach 250? Less than 29.8 years. In fact, it looks like it's not a lot less, but let's crank through the numbers. So we're interested in a population half the size of the carrying capacity, that is a population of size 250, we'll set the function equal to 250 and solve for t. Same manipulations we had before, divide both sides by 500. We get 200 over 500 equals 1/2. The fact we're talking half of the carrying capacity, and we get a 1/2 here, not a coincidence. Let's take a reciprocal of both sides like we did before. Reciprocal of the left-hand side produces this. Reciprocal of the right-hand side produces a 2. Subtract 1 from both sides, giving 83.33 times the exponential equals 2 minus 1 is 1. Divide that coefficient out. That gets the exponential function by itself. Take a natural log to get rid of the exponential function, composition of inverse functions. That produces on the left-hand side the exponent negative 0.162t, right-hand side, natural log of 1 over 83.33. Divide out the coefficient of t to produce this, as we've done several times before. Feed it to the calculator, and it produces 27.3 years. Does that make sense? Yeah, that's consistent with what we saw in the previous slide. It was 29.8 years, wasn't it, to reach a size, population reach a size of 300. This is somewhat less than 300, and the amount of time is somewhat less. So that's reasonable. It's not obviously wrong. And that's Precalculus 1 algebra. So that takes us from very beginnings of talking about functions and graphing lines and circles through logs, exponential functions, quadratic functions we encountered along the way. So you're good to go, and you're ready for Precalculus 2, where you'll start in there. We'll be addressing trig functions. The book approaches it rather in a similar way. They establish a library of functions, or they add to the library of functions the trig functions and the inverse trig functions, and you deal with graphs of those. You are well prepared. So have a nice day. Maybe I'll see you in Precalculus 2 someday, or calculus.